Hello, my name's Rob McCullough. I'm with the R&D team at AD Metro. I'm speaking today about touch technology, and in particular, an innovative projected capacitive, or PCAP controller, that we've recently developed. AD Metro was founded over 25 years ago and has been innovating in touch technology ever since. In the early days, it was fitting touch sensors to curved CRTs. Then the company patented armored resistive touchscreens using a thin layer of hard glass to ruggedize so much that these sensors remain popular with the military today. In 2016, we took a first stride towards simplifying PCAP touch, introducing a controller board capable of accommodating a wide range of touch sensors. In 2018, we released an advanced linear correlating infrared touch sensor, and in 2020, a 2-touch 5-wire resistive controller. The new ARGON adaptive PCAP controller is our latest innovation and the subject today. In case the touchscreen world is new to anybody, there are arguably half a dozen mainstream touch technologies. They all have a sensor part that fits on or around the display and a controller board or electronics that translate sensor contact into touch coordinates for the host system. Technologies that we sell include surface acoustic wave, surface capacitive, optical, infrared, plus the most prevalent two technologies, the ones we see most often. One is resistive touchscreens, generally single touch. They need a bit of contact pressure to activate, and they reflect a bit more ambient light, so underlying displays often seem dimmer. Finally, there's popular PCAP touch technology that you see in tablets, laptops, and most phones, with its attractive qualities of multi-touch, zero activation force, and high contrast. So here's a picture of the PCAP touchscreen controller that we call ARGON. This controller takes a big step in making PCAP touch systems easy to integrate and manage, simplifying the connection and compatibility issues, and offering a solution to uncertainty about electromagnetic and RF interference. Our observation from being in the touch business for a generation is that there are many opportunities to improve PCAP compared to other touch technologies. There are 4 main challenges facing PCAP touch systems. The rest of this presentation dives into how ARGON eliminates these difficulties. First, different size PCAP sensors have different numbers of rows and columns in their transparent conductive matrix. Even sensors of the same size do sometimes. Sensors are also designed with different orientations and different ordering of their conductors on the flex tails. There are good reasons for these things, fitting the sensor to the target product and managing interference and signal crosstalk issues. But these become issues for the integrator and then for the integrator's company throughout the company's entire product lifecycle. Second, a company might want to make just the simplest adjustment to their touch system operation. For example, one might want their product to use 2 touches instead of 10. For small companies using PCAP, I often see these details becoming frustrating issues. Their options are to acquire, install, and learn an oblique utility program, or to get support from their supplier and suffer lengthy shipping delays. There's a third problem with PCAP that's really in a different category. When integrating a PCAP sensor into a product, it's difficult for the integrator to know whether RF interference issues might be a problem when deciding how to mount the sensor and run the wiring. It's hard to decide, for example, how closely a PCAP sensor can be installed to a display. With some displays, if you bring the touch sensor too close, the touch system generates false touches. A display that generates less interference still leaves the integrator guessing. They must trade off between a thicker display and reliability, often based only on an educated guess. There are tools, utility programs, available to help, but they can't give definitive measurements. Even if they can run in situ on your host system, now your host system is running differently. And many utilities programs are Windows only, so entirely different equipment needs to be introduced to take these RF measurements. As a result, the test results using any available methods today are misleading at best. Finally, we address computer security. We've designed barriers into our controller to ensure that it can never be part of a hardware hack. These are the 4 issues that we address with the ARGON controller. A completely unique capability of the ARGON controller is that it automatically identifies and adapts to the connected PCAP sensor at the press of a button. That's pretty revolutionary in the industry. The cost and challenges of acquiring, storing, updating, coordinating, and loading firmware all disappear. The controller board itself has the popular 2x51 flex tail connectors. If you want to use a PCAP sensor with a different connector tail, say 68 pin or 2x50, we have little adapter boards to make the connection. Here's an example of the ARGON controller sensor adaption at work. It's connected to a 24-inch sensor now, and we'll be moving the board over to a 12-inch sensor. And powering it up, connecting the USB at the same time. It's still configured for the other sensor, so the controller doesn't work right. Press the Learn button. Blue LED flashes while the ARGON identifies the new sensor. The blue LED is steady again, and the new sensor works with the controller. If you already integrate PCAP Touch into your product, you'll immediately understand the benefits of an adaptive controller. Design effort and expertise built up can be reused. The touch aspects of your project development can be moved forward in your timeline, and importantly, the risk of compatibility mix-ups is slashed. I can't reveal everything about the adaption algorithms. Primarily, the controller counts the rows and columns of the sensor and looks at other distinguishing characteristics of the frame signals. In many cases, the controller then has all the information it needs. Either the sensor has been identified before, or the controller is pre-configured with knowledge of that sensor. Sometimes several touches of the screen are needed after the normal learn process if some ambiguity remains to be resolved. The ARGON controller has two built-in features to allow touch settings to be adjusted. One allows any configurable setting to be changed. I'll discuss that feature in a few minutes. For now, in recognition of the fact that changing sensor orientation is typically the only configuration change that's ever needed, I'll demonstrate the ARGON's QuickFlip feature. This feature allows the orientation of reported touches to be adjusted in seconds. There are two ways that this sensor can be attached to this display. And then operating systems sometimes apply their own orientation transformations. So there's several reasons that orientation sometimes needs to be adjusted in a touch system. So here we use QuickFlip, touch in the corner for several seconds, press the button, the orientation is being updated. As I mentioned earlier, the ARGON has another built-in tool to allow all the finer touch settings to be adjusted. All the typical adjustments can be made: maximum number of touches, sensor sensitivity, orientation again, mouse simulation, and more. Holding the Learn button for several seconds starts what we call settings mode. Touches are not forwarded to the host computer during settings mode. Instead, the touch sensor is used to input new touch settings to the controller. To guide where to press the sensor to make adjustments, we supply what we call button maps. These are JPEG or printed images that show the buttons available in settings mode. So here's a picture of a button map, just a JPEG image or a paper image that shows where the buttons are when you're working with settings mode of the ARGON controller. And here's on the left the 5 steps to make a change using this ARGON feature. Displaying the button map or referring to the button map is the first step. The second step is to press and hold the Learn button. Then you're in settings mode, so you touch the top of the display to activate all the remaining controls. Now you can make perhaps a change to 2 touches or increase sensitivity. And the last step is to press and apply the selected settings. They take effect in just a few seconds. Here's a demonstration of an adjustment being made to touch system operation using the tool built right into the ARGON controller. In this case, the maximum number of touches is being changed from 10 to 2. The first step is to display or refer to the button map. Then, to enter settings mode, the Learn button is held for a few seconds until the green LED flashes. The top bar of the screen is touched, the 2 touches button is pressed, and the Apply Settings button is selected. The settings take effect right away, and the touch system is back in operation. Under the wrong conditions, electromagnetic or radio frequency interference can disrupt or generate false touches from a touch system. The ARGON controller has state-of-the-art immunity to RF interference, but PCAP sensors are made up of long electrical conductors and get installed as close as possible against displays and other electronics that generate interference. We've created the ARGON controller with a built-in tool to help integrators. This interference tool indicates the level of interference being experienced compared to signal levels that can initiate a touch. With this tool, integrators can now know where they stand in terms of the risk of false touches. Because the tool is integrated right into the controller, measurements are an exact reflection of real touch system operation. Further, being built in, the tool is always available, so integrators can check for interference while exercising all the different ways that their product or nearby systems might operate. The ARGON interference tool is started by holding the Learn button as power is applied to the controller. While the interference tool is operating, the controller doesn't forward touch locations to the host system. Here's a sped-up demonstration of the ARGON interference tool in operation. Here it's being activated. It shows green flashes when the sensor is against the modern laptop display. And here against an older display, and full disclosure of some ground loops in the wiring, there's some red flashes. At a spacer, it's green flashes again. The flashes quantitatively represent the signal-to-noise ratio, but that's not really clear in this video. And the indication is red again with the spacer removed. A novel feature of the ARGON controller is its security filtering. USB and other communication connections are becoming more prevalent mechanisms for hacking into systems. Our solution is to arrange that the only communication between the ARGON controller and a host system is through the firmware developed in our facility and running on our domestic microcontroller. There's a white paper on the AD Metro website that details this issue. The ARGON controller easily connects to host systems via USB, I2C, or RS-232. The ARGON helps speed PCAP touch product development in several ways. First, compatibility is assured, so there's no need to wait to learn sensor size, orientation, controller sensitivity settings, for example. Second, the controller can be reconfigured in place. So if there is a mix-up, it takes minutes to correct instead of perhaps weeks. The ARGON has all the features you might expect from a PCAP controller and more. The ARGON controller can be seamlessly substituted for conventional PCAP controllers already sold by AD Metro. With sensor adaption, QuickFlip, built-in configuration, security filtering, and a built-in interference tool, ARGON makes the hard work of PCAP integration easy. Thanks for listening.